Dilution formula, students. Suppose if you want to convert higher concentrated solution to lower concentrated solution, you can use this formula. What is that formula? M1V1 is equal to M2V2. M1V1 is equal to M2V2. Here, M1V1 are the molarities and volumes, initial molarity and initial volumes of the solution, and M2V2 are the final molarity and volumes of solution. Suppose they are given 200 ml of 2 molar solution. 2 molar solution. From this, they want to prepare 0.5 molar solution of 0.5 molar solution. For that volume, how much we have to increase, that we have to find. So here, M1 is 2 molar, V1 is 200 ml, M2 is 0.5 molar. They want to prepare 0.5 molar. V2, how much we have to raise? So M1 V1 is equal to M2 V2. If you here 2 into 200 is equal to 0.5 into 0.5 into V2 is equal to 0.54 times 800. So we have to make this volume 800. How much water we have to add, students? This how much water we have to add? Anyone can you tell? This how much water we have to add? You have to make resultant solution 800 ml, right? Already 200 ml is there. How much you need to add extra?
600.
600. So amount of water to be added is equal to V2 minus V1. If you do, you will come to know V2 minus V1. Now to make the volume to 800 ml, to dilute this one from 4 molar, 2 molar to 0.5 molar. Nothing is there. Concentration decreased to 4 times, right, students? 1 by 4 times. So volume you have to increase by 4 times since concentration is inversely proportional to volume. Same thing we can use for we can use in terms of normality also. And relation between molarity and normality, we'll see. Relation between molarity and normality. How to convert molarity into normality, normality into molarity. This one also important, students. For solving problems and all, you need this. Relationship between molarity and normality. First, write the formula, molarity formula. Weight by gram molecular weight into 1000 upon V in ml. Normality formula is weight by gram equivalent weight to 1000 upon V in ml. Just take the ratio, students. Molarity by normality is equal to this 1000 by V will get cancelled. Weight also will get cancelled, isn't it? Otherwise, one will time. 4 divided by 1000 by VML will get cancelled. Even weight also will get cancelled. 1 by gram molecular weight, 1 by gram. So gram equivalent weight by gram molecular weight. M by N is equal to 1 by N will take students. N factor will consider. N factor. N factor we have to take. So now normality is equal to N into molarity, where N is actually N is nothing but gram molecular weight by gram equivalent weight. This is N factor, where N is N factor. I said no. This N factor, what and all includes in this? Basicity of acid. If it is acid, basicity we have to take as N value. Or acidity of base. If it is base, acidity of base we have to take. If it is salt, charge on ion. It is used to determine concentration of unknown concentration solution by titrating or reacting it with a known concentrated solution. It's called titration. Solution whose concentration we know, it is called standard solution. By using standard solution, we are finding the unknown concentration of solution. So here, acid-base titrations we'll see. Acid-base titration is important. Acid-base titration. These are also called neutralization reactions. Neutralization reactions. See students, what is neutralization reaction? When equivalent number of H plus ions, OH minus ions are there. OH minus suppose base need equivalent number of H plus ion. H plus needs equivalent number of OH minus ion. So the number of equivalents of H plus is equal to number of equivalents of OH minus. Then only the particular solution will be neutral. And the reaction is called neutralization reaction. Neutralization
So
reaction.
can you please repeat that?
Sorry?
So you were telling something about H plus and OH minus ions. Can you please repeat that?
Yeah. Number of equivalents of H plus is equal to number of equivalents of OH minus, I said. Number of equivalents of H plus is equal to number of equivalents of H. Otherwise, number of equivalents of acid is equal to number of equivalents of base, you can write. Equivalents. In these cases, in acid-base titration, generally we use normality only. We'll get accurate one. Otherwise, you can use molarity also, but OH minus and base acidity is perfectly how to take. Otherwise, it will go wrong. Better you go use normalities. Generally, books also they use normalities only. They give in terms of molarity also they convert into normality. Now you got to know how to convert molarity into normalities. Then only to just equate this number of equivalents. Number of equivalents of acid is equal to number of equivalents of base. Students, you know, normality is equal to number of equivalents of solute by V in liter. V in liter. Otherwise, N is equal to number of equivalents of solute upon V into 1000. If you want to convert in terms of ml. So from this, number of equivalents is equal to N into V by 1000. N into V upon. See here, N number of equivalents of acid is equal to number of equivalents of base. We don't know. From this equation, we can write like N acid into V acid by 1000 is equal to N base into V base by 1000. 1000 anyway it will get cancelled. So from this what we can write, number of equivalents of acid is equal to number of equivalents of base. NaVa is equal to NbVb. NaVa is equal to NbVb. This is about acid. It's about this. Already I gave. So in acid-base titrations, what we do to students, acid versus base titrations we do, and suitable reagent indicator we'll add based on the pH of the solution. We'll select the indicator. That list, if you want, I'll give indicators list. It will come in acid-base chapter. Indicator we'll use because it gives the color, particular color to the solution. Generally, acid-base solutions are colorless solutions. We can't come to know the end point. To find out the end point, indicator we use indicator gives the color. Once if base acid and base get neutralized, no color of the indicator will change. Sometimes color will changes to some other color, or sometimes it changes to colorless. Depends on the indicator. So that is the end point. That is the end point where color of the solution disappears or changes. So, what is diffusion, students? This diffusion is spontaneous only when the spontaneous movement of high concentration to low concentration, movement of a substance from high concentration to low concentration. It is called diffusion. So leakage of LPG, leakage of marsh gas, all these are the examples of diffusion. And suppose two gases, just it is one application, students. From this end, I am sending ammonia gas. From this end, I am sending HCl gas. Once NH3 and HCl, if both meet, no, they form ammonium chloride, which is in white color. White precipitate will form. So now this is the exactly center of this tube. Center of the tube. When I allow ammonia gas from this end, HCl gas from this end, this ammonium chloride will be formed. No, that white precipitate will form closer to HCl or closer to ammonia. Understood? These are one of the applications of diffusion. So, like I told you, lighter gases can diffuse faster than heavier gases. That was given by Graham's. Rate of diffusion is inversely proportional to square root of density. Rate of diffusion is, you can also write in terms of molar mass. Inversely proportional to square root of molar mass. In states of matter, you will get this one. So here only definition and solution enough. Solutions enough. Osmosis is nothing but movement of solvent particles from lower concentration to higher concentration through semi-permeable membrane. Through semi-permeable membrane. What are colloidal solutions, students? What is colloidal solution? What is the difference between true solution, colloidal solution, and suspension? Difference among true solutions, colloidal solutions, and suspensions. In true solutions, particle size is too small, less than 10 to the power minus 7 centimeter. Particle size is less than 10 to the power minus 7 centimeter, or sometimes we tell less than 1 nanometer also. 1 nanometer. Here, in case of suspension, particle size is greater than 10 power minus 5 centimeter, or greater than 100 nanometer. You can use greater than 100 nanometer also. Now, colloidal size, colloidal solutions, the particle size is in between true solutions and suspension. True solutions and suspension. So, the particle size here in between 10 to the power minus 7 to 10 to the power minus 5 centimeter. Colloidal solutions in which the particle size varies from 10 power minus 7 to 10 to the power minus 5 centimeter. These are colloidal solutions. These are in between, this particle size is in between true solutions and suspensions. Bigger than true solutions, smaller than suspensions. In the solutions, how solute and solvent exist. In colloidal solutions, there are two components. One is dispersed phase and dispersion medium. Dispersed phase and dispersion medium. In suspension, colloidal particles will be settled down after some time. True solutions you can't see only. What about colloidal solutions? Colloidal solutions, friends. The solute particles will they settle down?
No.
No, particles do not settle down. Solute particles, they are continuously, they are in settle down. Next one, colloidal solutions. The colloidal particles carry charge. These solutions are charged solutions. These are electrically charged. Electrically charged. Next side heading, students. Types of colloidal solutions based on phase of dispersed phase and dispersion medium. Dispersed phase in dispersion medium. Dispersed phase, dispersion medium. It is like a solvent, students. Dispersed phase in dispersion medium. Now, dispersed phase is gas, dispersion medium is gas. Which type of colloidal solution it is, students? Dispersed phase is gas, dispersion medium is gas. First of all, it is not a colloidal solution only. Gas in gas is homogeneous mixture. It is true solution. It is not colloidal solution. Okay. So, and one more thing I wanted to tell you. If dispersion medium is gas, students, those colloidal solutions are called aerosol. A, you remember, aerosol. Dispersed phase can be solid or liquid. If you want to distinguish solid and liquid dispersed phase, you can use solid aerosol. Next one, this one also aerosol. Example for first type is smoke. Liquid in gas. Solid in liquid. Liquid in liquid. Gas in liquid. Gas in liquid. Solid in liquid is called sol. You can also write solid sol. CET and all. Among the following, which is gel, which is emulsion, like that they are asking. And based on classification based on interaction between dispersed phase and dispersion medium. Second classification based on the interaction between dispersed phase and dispersion medium. Interaction between dP and dF. So first type is lyophilic colloidal solution. Lyophilic colloidal solution. Lyo means, anyone can tell, students? Liquid. Phile means love. Liquid loving groups, simply you can tell solvent loving groups. If dispersed phase and dispersion medium, dispersed phase, if it is having more interaction with or strong affinity towards dispersion medium, then such type of colloidal solutions are called lyophilic colloidal solutions. If dispersed phase has strong affinity towards dispersion medium is called lyophilic colloidal solution. This first phase has strong affinity towards dispersion medium. Dispersion medium. Then the solutions are colloidal solutions are called lyophilic colloidal solutions. Yes, this type of colloidal solution directly we can prepare, students. Directly we can prepare. Example, starch solution. Starch, if you dissolve it in water, it will mix. It will mix. Means it won't dissolve 100%, it will mix. Directly we can prepare. And rubber solution. By taking suitable solvents, we have to prepare. Gum and all we can, these are all examples of gum solution, starch solution, gelatin solution. All these are the examples of rubber solution. All these are the examples of lyophilic colloidal solution. Okay, ma. Next one, lyophilic colloidal solution over now. Lyophobic colloidal solution. Lyo means same. Here also liquid only. Phobic means hate, hating. Liquid hating means this disperse phase doesn't have proper affinity towards dispersion medium. Dispersion medium. Example, metal salts. Metal salts. Suppose gold salt you want to prepare. Directly, if you add gold to the particular solvent like water and all, it won't dissolve, it won't mix. So it is hydrophobic or lyophobic. Okay, metal salts, metal sulfide salts, all those are the examples of lyophobic colloidal solutions. These colloidal solutions, disperse phase has not uh, having any affinity towards dispersion medium. Doesn't show any affinity towards solvent or dispersion medium. Dispersion medium. So this type of salts directly you can't prepare like above salts. You need to use special methods to prepare lyophobic colloidal solutions. So direct mixing is not possible. Metal, if you want to, suppose gold salt, if you want to prepare, you have to pass immense heat. Then only that gold will melt afterwards. It will evaporate and it will mix with the solvent. Otherwise, it won't. That is called Bredik's arc method. That and all now beyond your scope. In second year, you are going to learn. So special methods can be used to prepare lyophobic colloidal solution. Best example for lyophobic colloidal solution is metal salts. All metal salts are the lyophobic colloidal salts. Metal salts and metal sulfide salts. are the examples of lyophobic colloidal solution. Next, one more property, students. Lyophilic colloidal solutions are reversible. These are reversible. Important property I forgot. These are reversible in nature because they have affinity. If solvent evaporate also, again it will interact with the solvent, so the process will be reversible. Lyophobic, this process is irreversible. Once if they get precipitate, no, it won't give again colloidal solution. If it settle down, it will not give spirit. So lyophobic colloidal solutions are irreversible because we are applying special methods and we are preparing this one. Once if it get precipitate, no, we can't get back this colloidal solution. So these are irreversible in nature. Okay, students. These are the based on the interaction between the lyophilic and lyophobic, interaction between the disposed phase and dispersion medium. Colloidal solutions are classified into lyophilic and lyophobic colloidal solutions. Next, another classification, last classification, based on the type of particles of dispersed phase, based on the type of particles. Third classification based on type of particles. Classification based on type of particles. First one is multi-molecular colloidal solutions. Multimolecular colloidal solutions, macromolecular colloidal solutions, associative colloids. Multimolecular, macromolecular, associative colloidal solutions. Multimolecular name itself you can make out. Multimolecular means number of particles will join together and form colloidal range particles. Suppose small particles, if they join together and form colloidal range particles, then it is the solution formed in this way. Those are called multimolecular colloidal solutions. When small molecules aggregate and form colloidal range particles, size in the colloidal range, that is 1 to 100,000 nanometer. Those are called colloidal solutions. Example, gold sol. Gold particles, small particles, they join together and form sol. That is called gold sol. Gold sol is an example of multimolecular colloidal solution. Sulfur sol. This tiny sulfur particles, they aggregate and form the colloidal range particles. The solutions formed by this type of solutes are called multimolecular colloidal solutions. Solution in which small molecules of a substance aggregate together to form species having the size of the colloidal range, having the size of colloidal range is called multimolecular colloidal solutions. Size 1 to 1000 nanometer. Otherwise, species having size of colloidal range. It's called multimolecular colloidal solution. Examples are important, students. Among the following multimolecular colloidal system or solution is macromolecular colloidal system is associative colloidal system is like that they are asking. You can write metal salts or gold salt is the better example. Sulfur salt. Next one, another type is macromolecular colloidal solutions. Macromolecular colloidal solution. Macromolecular colloidal solution means these particles looks like bigger size, but they are having they follow the colloidal range only. Example, if I give example, you can understand better than this definition. See, student, proteins are the polymers of amino acids. They are the polymers. Polymers means what we think they are the bigger molecules. Polymers. Starch, it is a polymer. Polysaccharide, it is polysaccharide. Polymers means many units join together and form a large molecule. Student. That is polymer. That small units are called monomers. Small units are called monomers. These polymers, if they the particle size it is big enough like colloidal particles, then those solutions are called macromolecular colloidal solutions. Macromolecular solutions. These macromolecule size is enough to form colloidal solutions, or their size in the range of colloidal particles only. Those are called macromolecular colloidal solutions. Size of the macromolecules may be in the colloidal range. Example, protein salts, starch salt, all polymers, whatever you can write. In second year, polymers topic is it. Even this one also, second PU topic on students. Macromolecules. Macromolecules in solvents, you write. Suitable solvents. Macromolecules in suitable solvents form solutions in which may be the range of colloidal particle size. Is called macromolecular colloidal solutions. Macromolecular colloidal solution. Example for macromolecular colloidal solutions are starch solution. All polymers, wherever you find polymeric form, you can take as a macromolecular colloidal. Starch salt, cellulose salt. Cellulose is also a polysaccharide, students. Cellulose salt. Simply you can write polymer solutions, natural and artificial solutions. Protein sol also you can write students. Protein sol is also an example of macromolecular colloidal solution. Protein is also one of the polymeric form. Next one, associative colloids. These are also called micelles. This one also important, students. Associated colloids or micelles. There are some solutions at low concentration they behave as electrolytes. At high concentration they behave like colloids. Electrolytes means which can ionize into ions and they pass electricity. Electrolytes at low concentration they behave like electrolytes. At higher concentration they join together. They join together instead of splitting. They join together at higher concentration. They form aggregate those aggregates and form colloidal range particles. Those are called associated colloids. Those are called associated colloids. Right now associated colloids. I'll show how it happens, and same thing we can use for cleansing action of soap also. Is application of cleansing action of soap. Students, I told at low concentration they behave as a strong electrolytes. At higher concentration they behave as colloids. The concentration above which they behave as colloidal solutions. No, those are called critical micelle concentration. Right now, critical micelle concentration, CMC. CMC for soaps and all they mention CMC, this range and all. CMC. Concentration above which micelle formation takes place, or at which also you can write concentration at which micelle formation takes place is called critical micelle concentration. Critical micelle concentration. In bracket you can write CMC. CMC. Even particular temperature also we required. You have to maintain a certain temperature also. The temperature is called Kraft temperature. KRAFT. Kraft temperature. Temperature above which micelle formation takes place is called Kraft temperature. Soap solution is one of the best examples, students. Associated colloids. Do you know the formula of soap, students? Well, no, simply you can tell sodium or potassium salts of fatty acids. Fatty acids. Stearic acid and all. C17H35 CONA. Those means long chain. C16 to 17 carbons are there. Now you can imagine how much it is. So long chains. You can also write like this instead of. Simply I wrote it's not exact number. This one is hydrophobic part. Hydrophobic part is nothing but hydrocarbon part. Hydrocarbons are not soluble in water. No, hydrophobic. Phobic means hating. I said. Little small I write. This part is there. This is called hydrophobic part, which is not soluble in water. This carboxylate part is there. No, hydrophilic. It is. It likes water. Otherwise, simply I write RCOONA. R is nothing but hydrocarbon part. Long chain is there now. That this is hydrophobic. This one is hydrophilic. It likes water. It dissolves. Okay, students. When this soap is in contact with the water, this is the water. This hydrophilic part will be attracted towards water. Hydrophobic part is away from the water. Away from the water. See here, hydrophobic part is away from the water. Hydrophilic entered inside the water. This carboxylate part is there now that entered inside water. After increasing some after increasing the concentration, what will happen? So one water molecule, water droplet I'll take. After increasing certain concentration or after reaching to critical missile concentration, this hydrophilic part, sorry, this hydrophilic part is there, no, it will pull the hydrophobic part also inside the solution because here concentration is more, no, it is getting more attracted towards the solvent. In that moment, it forces the hydrophobic part also inside the water and itself it will come out. Hydrophilic part will come out and hydrophobic part will go inside the water. Like this condition will be reversed. Like a now hydrophobic part went inside the water, means hydrophilic pull the hydrophobic chain inside the water. Now the cyclic formation is there, no? This is called micelle. Micelle. It happens only after reaching micelle concentration, critical micelle concentration. Only at critical micelle concentration happens. Other case, in the first case, it acting as electrolyte. Now it is acting as a micelle. Micelle. See students, once if we increase the concentration, same thing we apply for the cleansing action of soap. Sometimes they are asking in second year, explain cleansing action of soap. Cleansing action of same thing. Same this it will coagulate with the dust particles. This hydrophobic part, dust particles that oily and all like hydrophobic only. No, when we apply soap, they form like a these dust particles form micelles with the soap solution. After reaching certain concentration, like micelle formation takes place. No, this is like oil drop. Around oil drop like this, it form hydrophobic and hydrophilic form. After reaching certain concentration, it forms. No, when we dip it in water, this hydrophilic part, what it will do, it will pull that oil particle inside the water from the fiber. It will pull from fiber to what? How micelle formation took place? Same way it forms micelle and it will be remove. It will remove from fiber and it will take it to what? This oil. And the same thing you can apply for cleansing action of soap. So micelle will form like this. So what did I say? Some solutions that act as electrolytes at low concentration, at high concentration they behave in, like a colloidal solution. These colloidal solutions are called associated colloidal solutions. These are also micelles. Got it, students? How it is forming micelle? So definition if they ask, write like this only. There are some solutions at low concentration they behave as electrolytes. At high concentration they behave like colloids. These colloidal solutions are called associated colloidal solutions or micelles. Next one, coagulation of colloidal solutions. No, coagulation you don't put, students. So here I want to give first properties of colloidal solutions. First properties of colloidal solutions we discuss. Properties of colloidal solutions. First one is electrical property. Electrical properties. Tyndall effect. Electrical properties are also called optical properties. Tyndall effect. First one. Important students. What is Tyndall effect, students? Tyndall effect.
Scattering of light by the colloidal particles.
Scattering of the light by the colloidal particle. Why only colloidal particles are scattering, Tripti?
Because they are large enough to scatter the light.
Very good. In case of true solutions, particle size is very small. So, if you take true solution, light will move like this. If you take suspension, this is true solution. This will be opaque. It will not allow the light. And here, colloidal particles are big enough to scatter the light. Colloidal particles are big enough to scatter the light. When light is passed through colloidal particles, they scatter the light. They illuminate in all the directions like this. Okay, this can be observed. So light is illuminated. This property is called Tyndall effect. The scientist named after is called Tyndall effect. When light is passing through colloidal solution, the colloidal particle size is big enough to scatter the light, and light illuminates in all the directions. Illuminates in all the directions. That property is called Tyndall. This effect is called Tyndall effect. Scientist Tyndall observed this, so the is named after effect is called Tyndall effect. Only so sometimes they are asking how can you distinguish true solutions, suspensions, and colloidal solutions by using Tyndall effect. True solutions there is no scattering; directly light will go past in a single ray. Suspensions they are act like opaque. Only colloidal particles can scatter the light. So this is Tyndall effect. Tyndall effect. And one more property, Brownian movement. Brownian movement. Brownian movement. What is Brownian movement? These colloidal particles move in zigzag manner. Zigzag manner. The zigzag movement of colloidal particles, zigzag movement of colloidal particles is called Brownian movement. Here, Brown observed this movement, so is named after. It's called Brownian movement. So unbalanced bombardments of particles. This Brownian movement is due to unbalanced bombardment, collisions of the particles by the molecules of dispersion medium. Here, dispersed present dispersion medium particles. Those are unbalanced bombardments. Okay. Because of that, particles are these colloidal solutions, colloidal particles are moving in zigzag manner. So this Brownian movement will not allow the particles to settle down. Not allow the particles to settle down. This is only Brownian movement. Zigzag movement of colloidal particles. It's called Brownian movement. This is due to the unbalanced bombardment of colloidal particles by the molecules of dispersion medium. Okay, so remaining properties in 1 hour I need students. So within 1 hour I can finish next class.